In this video, we'll practice working with complex numbers. It's going to be pretty useful as we move throughout the course. And so for the first part here, we're going to just look at two numbers, 3 plus j times 2, and b here is 1 plus j times 2. Now the first thing to think about is, if I'm just going to add these two up, it's really straightforward. I just add the real part and the imaginary part. No problem. Same as subtraction, easy, so 3 minus 1. For the real part is 2, and the imaginary part, j2 minus j2, goes away. That's really easy. So here we are in rectangular form. Addition and subtraction are easy, but what if instead I'm interested in a times b? Well, in this case, it's not quite so straightforward, right? What is straightforward is to think about if I knew the magnitude and phase of those two numbers, then the magnitudes are going to multiply, and I can just add the phases of those. And when I say the magnitude and the phase, of course, you can think about our complex numbers being on a real and imaginary plane. And so, for example, 3 plus j2 has a real part of 3 and an imaginary part of 2. So it looks a little something like that. And so the magnitude, of course, is that magnitude, and the angle there is the angle from considered 0 degrees here, or radians. So there's the angle. So in this example of a times b, we have the magnitude of a is the real part squared plus the imaginary part squared. The magnitude of b is the real part squared plus the magnitude, the imaginary part squared. And then the angles, the inverse tangent of the imaginary part, right? The imaginary part over the real part, so that's 2/3 plus the angle of b, which is 2/1. And of course you could figure out what that means. Similarly, for if we want a minus b, much easier if we have the polar or magnitude and phase representation of these numbers. And if we did, we can just divide the magnitudes and then we subtract the phases. So in this case, again, the magnitude of a is the real part squared plus the imaginary part squared, and we take the square root. Same for b. And then the angle is the inverse tangent of 2/3 minus the inverse tangent of 2. Great. One other way of representing numbers that have a real and imaginary part is by using Euler's formula that we've looked at. And so now let's consider if we have a number that is given in this complex exponential form. And so it might be something like this. We could have another number that looks something like this. And if I'm looking at, okay, how do I deal with these two numbers? Well, we use Euler's formula. So C is equal to, the magnitude is 3, and then we have cosine of pi over 2 plus j sine pi over 2. And that just equals 3. Cosine of pi over 2 is 0. Sine of pi over 2 is 1, so we just have 3 times j. So if we want to go from this magnitude and phase form into a rectangular form, again, we can use Euler's formula. So for d, we end up with 2 times cosine minus pi over 3 plus j sine minus pi over 3, 2 times cosine of minus pi over 3 is a half. This is root 3 over 2 minus root 3 over 2. So we end up with 1 minus j times root 3. So if I wanted to multiply these two numbers together, c times d is really easy. 3 times 2 is 6. And then I want to add the phases, and so that's pi over 2 minus pi over 3. If I want to add them, then it's much easier to do this form where I would then have 1, right, plus the real part of this one's 0, plus j times 3 minus root 3. So when you're doing these manipulations, this algebra with complex numbers, think about whether you want them in the rectangular form or the magnitude and phase form, because it can make it a little bit easier.